All right, let's get slowly started. Uh, we'll be recording this class, so not the video, but whatever I'm showing on the screen, plus my voice and any questions you may ask for whoever didn't show up today and may want to take this class later. And so don't let that discourage you from asking questions. I hope that this will be really conversation. Since we have only 5 people, there will be a nice opportunity to have a completely different class than I have planned. All right. Anyways, my name is Marcin Żurkowski, and I'm part of the research computing group in the IT organization. I have seen most of you on many classes that we organize. This is a class that's a little bit different than our usual classes. Usually we organize trainings for platforms that we really support. So like Palmetto, and we do something related to Palmetto. We do a little bit around research computing, introducing people to research computing techniques. We do a lot of trainings for related to data science, generally defined, again supporting our platforms and introducing different tools that are related to particular field of research. This class is truly an introduction to a language, and I assume that everybody knows how to program. Who doesn't? Who never ever programmed before? All right, great. So we'll quickly run through. This class is designed for 8 hours, and I'm sure we don't get through everything that I planned. Today we'll have 4 hours, and I planned also 4 hours for tomorrow. If you're very welcome to come tomorrow, and I hope that you will. Anyways, all the materials for this class you have on the webpage that I showed you a second ago, and I'll show you in a second one more time. There is a directory there called PDFs with about 18, 19 handouts for this class. So everything that I'm showing on the slides is also in these PDF files. You don't need to download the slides. It's exactly the same things, a little bit different organized, but you have everything. We also have about 60 tool programs that we'll go through over these 8 hours. And I hope that these programs will be reference for your future work. So don't really study them now line by line, and don't try to understand everything, remember everything, how to do. Treat them as a reference, treat them as a cheat sheet, as programs that you can steal from in the future. All right, so tell me a little bit about yourself. Why did you come to this class? Why do you want to learn Fortran? And I'll tell you how I learned Fortran. I joined a research group, and during my first week, I got assigned some task, and I had no programming experience before. My background is chemistry, so chemistry is a field that doesn't really have strong computer skills in the curriculum, and people need to learn things while they enter some research. So I had no programming classes, and when I joined the research group, I was given Fortran 77 code and said, all right, this is what you have to do. This is the science problem. This is the code, modify it. Oh my God, what am I going to do now? So I sat down, I had to go line by line. People were laughing at me that I'm learning Fortran because Fortran 77 looked like sort of a Commodore 64 type of language. But, well, that was my first interaction with Fortran. And I had to learn it because there was a lot of work done in Fortran prior to me joining that research group, and that was the traditional programming language for my field. So now, X years later, most of the programs in at least my field are still in Fortran. Why? Because this is still the easiest and the fastest way of getting high performance from your calculations from machine. Now, what about you?
Actually, it sounds sort of similar to what you said. So
okay.
I also have a chemistry background.
And so a lot of the programs that I've come across have used Fortran. And so I haven't had to actually go in and modify anything. But just for me, it's I've played around with Fortran before, and I liked it. So it made sense to me. So I'm sort of just looking forward to learning more and actually be able to sort of maybe modify some of those programs that I've run across.
Okay.
Down the line.
Over there.
Yeah, pretty much the same thing. I'd like to modify some programs and implement some functionality that I would like to add. So to be able to write Fortran language that the program's already written is pretty necessary.
Okay, so exactly the same story. You're also chemical engineer. Yes, there you go. What about over there?
Mostly curiosity.
Curiosity?
Also, I think Fortran is I'm from the engineering department.
Okay.
So engineering, computer science, Fortran is a really bad reputation. Like, it doesn't deserve it. I think it's a great language. It's trying to computing. It's almost something faster than C, and C that people see a lot of optimization is excellent. I want to learn more about it.
Okay. What about over there?
Same reason as
Yeah, so you touch on a very good point that Fortran has bad reputation, and we'll talk a little bit about that. You joined the last, so let these people go first. What about you, Marcus?
I always like to program and learn new language. I know a lot of them, I know another language, but Fortran always caught my attention. I don't know. So, like, if I have the opportunity to be in a workshop where I can get that introduction, it's easier instead to take a book and read by myself.
Sure.
So it's a good opportunity to learn and to have a base of platform in order to study more in a few days or weeks or when I need it, basically.
I'm from physics department, space physics group, and recently I realized that most of the models that were written many years ago are still being written. All these models are written in Fortran. Also TCM and atmosphere models now, they all were written in Fortran. I started to run these models.
Sure, great. And you?
From mechanical engineering, I'm using Fortran right now. I learned it by myself, like searching, reading tutorials and stuff. So I wanted to learn it better, and that's why I used it.
Sure. All right, so we have, at least a few of us have the same story, that there was you joined the group and there is some legacy work that you need to start either modifying or at least be comfortable with, and that's been done in Fortran. And that's most common for all people joining Fortran now. I'm glad that you guys are here. You don't really have, are forced to learn Fortran, but I'm glad that you're curious. Okay, so please, if you didn't yet, please go to this address. It's a GitHub repository with everything that I will be using during this class today and tomorrow. All the programs that we'll be using are there. All the handouts are there, or examples, and you have everything available immediately. All right, so why Fortran? Is that Fortran has a really bad reputation, and why? It's not taught at university anymore. Nobody at Clemson teaches Fortran anymore.
Fortran 9 is the column on the column. It's the old mainframe language, so column numbers are significant.
The fixed format is prior to Fortran. Prior to the Fortran 90, there was a fixed format required.
IO unit number is probably scared.
Yeah. People generally think that this is a very old language and doesn't have any modern tools. So it's not like people think that, all right, it's not like Java, like C++, like any other object-oriented program that has all the nice functionalities, and that it is something that was developed 50 years ago and never touched after. And that's actually not true. Fortran is actually a very old language. It started in 60s and it gradually developed since then. But since 90s, it has been a lot of work done on Fortran, and a lot of modern concepts from computer science are present in Fortran. So pretty much everything that's doable in C, Java, all the nice concepts of object-oriented programming are also present in Fortran. Fortran gets a little bit less attention from computer science departments and a little bit more attention from people that need to implement mathematical models to do some real work. And the reason for that is this. It's a little bit rigid language. It's a little bit, maybe a little bit, has this legacy of things that are assumed. It has all the nice features, but it has all the mathematics built into itself. All mathematical functions you can pretty much that you will be required using in most of the models are built into Fortran. And they're not part of C, they're not part of C++, those are external libraries there. It's difficult to expect, for example, a Bessel function to be part of new language. Go doesn't have a Bessel language, Bessel functions built in. It may have missing a lot of mathematical functions. It has also built-in operations on arrays, element-wise and cumulative operations. So it is really that thing that made Fortran this formula translator and made it easy to bring mathematical equations into a computer program, made Fortran very popular among scientists and engineers. And that's where it's mainly used. There is a huge number of legacy codes. Pretty much each of us started with code that was written by prior members of our groups, and that was done in Fortran. Now we have to modify it. We need to at least learn how to read Fortran. You can start rewriting everything in language you're more comfortable with, but at least you need to read what other people did, and you need to really understand what things, what different parts of this program are. It's very easy, or at least reasonably easy, to get very good performance out of Fortran due to build assumptions in the language. So if you start writing a code, let's say we'll start writing a computational fluid dynamics, whatever, something we have no experience in, and we'll start program from scratch. We have the initial version in Fortran and in whatever language you name it. I can safely assume that the version in Fortran will be faster. And it's not because we did anything on purpose. We did anything special to target performance. It's about this assumption that Fortran has about how things need to be done to get good performance. And those are the assumptions of the language. That's why Fortran is often referred to as a little bit faster than even C, because C is missing some of the assumptions. Again, many mathematical functions and basic algebra are inherent part of the language. They are built in. They're not external libraries to the language. Fortran has a very rich syntax. It has a lot of keywords, a lot of functions built in. Contrary to C, for example, that has about 20 keywords and that's it. It's very basic language, very compact. Fortran has hundreds of keywords. You don't need to learn everything. There is a lot built in into Fortran. Now, we touched about the fixed format, which made it look a little bit old comparing to other languages. Modern Fortran is very easy to read. It doesn't need to follow this fixed format anymore, and you can write as you wish. And there are again some assumptions that make Fortran language very easy to read. And the last thing, there is just nothing wrong with Fortran. Fortran is a language like any others, and it doesn't deserve any reputation of being this very old, rigid thing. It is good language for what it was designed for. Now, if you start, depending on what you want to do, if you want to write a program to parse a web page and do some database based on that, some other language, it may be faster in any other language to get this program from the beginning to end. In Fortran, you may need to write a lot of things yourself. So starting with Python or something like that may be easier. If you want to, for example, implement this computational fluid dynamics, it may be actually faster in Fortran than other languages. All right, so let's quickly go through the outline of this class. We'll start with some basic things. We'll go through quickly run through the whole language and say what's important in any language, and after that, we should be able to program in actually any language. So we'll go through the concepts of programming. After that, we'll go to best programming practices, what actually should be done. We're scientists and engineers here, so treat this class as something that will teach you how to write software for research, not software for software, not software for other people that you won't be using. It is something that's like a hammer. You need to use it later on your daily basis. So you need to be really comfortable with what you want. Not only with a week or 2 weeks from now, but also at the end of your graduation when you need to move to other projects, when you actually need to hand this code to other people, or years from now when you want to go back to it. All right, after that we go through data types, loops, conditional statements, arrays, functions, subroutines, intrinsic functions. We'll go through modern concepts of overloading functions and subroutines. We'll go through I/O. That's also contrary to other languages built into Fortran. It's not external library. I/O is built in. We'll go through user-defined data types and basics of object-oriented programming in Fortran. After that, we'll go to modules, controlling the program, how to actually write nice program that will parse all the command line arguments, that will get variables from the operating system, so on and so on. We'll go through details of using preprocessor in Fortran. We just not think that it's inherent part of Fortran. This is something that the compiler supports, and it is very useful to make codes usable. We'll touch on that. We'll go through the CPU and wall time functions, how to actually time your work. After that, we'll go through pointers, and at that point, we'll forget about Fortran and start doing some things around programming. So we'll talk about makefiles, how to write makefiles, how to make building process automatic. We'll talk about mixing C and Fortran and how this should be done so it will always work. And after that, we'll talk about compiler options, which we'll go through compilers. We'll go through GCC and Intel compilers. We'll see what are different things, what should you expect from a compiler and what not. And the last thing we'll talk about is BLAS and LAPACK that are truly mathematical libraries for basic linear algebra and basic matrix, basic algebra operation and basic linear algebra operation. If there will be something that you're missing, raise your hand, we'll talk about it. And if you have any questions, please interrupt me and we'll go through something. Please use that repository. We'll do less things hands-on, and I'll spend more time talking about different things. And I expect that you will actually follow these programs. You will try to compile them yourself in the background. We'll establish how to do it in a second. And when you have problems, when something is not really clear, say, wait a second, something doesn't work. So, all right, let's introduce any programming language. if you want to start learning any language, yes.
How can I get these slides?
The slides are not available. You can get all the materials from this address. So if you go to this address, there will be a directory there called PDF, and there you will have all the handout for this class. There'll be about 19 files there. So if you go to this address, the https github.com /zio Fortran class, it will be GitHub repository. You can clone it. You will have everything in your directory. All right. So whenever you want to learn any language, this applies to Fortran or anything else, you only need to learn You need to learn 5 things. The first, what is the general structure of a program? How does it look like? How the most basic program looks like? And this can be truly hello world. This can be something more complicated. You need to know that how the program starts, how the program ends, whether it needs to be interpreted or compiled. How does the most basic program look like? After that, you need to know how to handle variables, how to do conditional statements, how to do loops, and how to define functions. When you learn these 5 things, you're good to go and you're ready to program in any language. So this is true about Fortran. About C, you need to know who is comfortable with C. Who's comfortable with Python? All right, most of you are comfortable with Python. So let's go through Python. You need to know how the general program looks like. You need to know that it is interpreted, that it requires a file that will be interpreted or some commands. You need to know how to define variables and how variables are handled, whether you need to assign a type or not. So in Python, you don't need to assign a type. You need to know that, for example, everything, the code is structured in blocks. It requires to be intended, and the blocks of the code are defined that way. You need to know how to make a comment, and that's it. Definition of variables. I said that conditional statements, again, there is this block of the code. You need to know how to write an if statement. Loops, again, the basic for loop in Python is enough for everything. Functions, you need to also know how to define a function in Python. Knowing these 5 things, you're really good to go, and you can start programming basic programs, and then you learn things as you go. So those are also the same things we need to learn about Fortran. And the most basic program in Fortran looks like this. Now let's go back a little bit. Most of the things we will be talking about today are in Fortran 90 or 95. People usually refer to them now as together as one combination, say Fortran 9095 rather than Fortran 95. To use this assumption, this only means this, that the program is not in a fixed format anymore, and it doesn't require this rigid structure. There is a lot of new concepts built into the program, into the language, but the basic keywords are backwards compatible. So whatever you learned about Fortran 77 in the past, whatever you see in older versions of Fortran, most of it is backwards compatible, and you can use that code. You can put it in part of your program, and you will be good to go. It will work. There will be some things I'll use from more modern versions of Fortran. There will be few things from Fortran 2003 and 2008 that we'll touch on, and but most of the things will be truly Fortran 1995. All right. So the basic program looks like this. Program, some name, print hello world from Fortran, and then end program hello. And that's the most basic hello world type of programming. Every program needs to start with this statement. Program, and then its name. Whatever it is just the name of your program. And after that, end program flow. So this defines the main and the only part that will be executed. Your when you prepare everything, you start running your program. The computer will go through every single line between this in this block, and nothing else. And the same may be done by some compilers. Compilers may actually only go through basic through only this block and compile, look at only things that are executed in this block. They won't be looking at different things. So everything that you want to do needs to be between these lines, between these two lines. The beginning of the program. Sorry for that. The opening sentence and the ending sentence of the command print star, comma, and some text encapsulated in the quotation marks will print that text on the screen. So this will be the basic hello world program in Fortran. All right, so how to actually get that to work? We need to create a file, and for consistency, we'll keep extensions of the files as versions of the Fortran we are using. I will be using small f90 or small f some number for all the files, and that's the convention now, or that's the most commonly don't think that if you're writing Fortran 90 code, you give an extension .f90, either small f or capital F, depending on what you like. If you go to, if you want to give an indication that you're using older versions of Fortran, you just keep .f. The same with newer versions of Fortran, Fortran 95, 03, or 08, you'll give the extension for a proper number. Right? So what we need to do is to first create file with all these 3 lines, and after that we need to compile the program. It's not like Python. It's not like it's not an interpreted language. Fortran actually requires a compiler, and in a second we'll say what compiler actually does. But for the moment, let's only take this. We need a compiler to translate this human readable file to machine readable file. And after that, you can execute the program. Right? So you can safely do all the all your work on Palmetto. It has number of Fortran compilers. If you look at the list of modules, you won't actually see a Fortran name there because Fortran compiler is a part of a bigger compiler package. What you may see is are 2 names. One set of modules will start with name GCC, which stands for GNU Compiler Collection, and there will be different versions of that. Or you can look at compilers starting with name Intel, and that's again Intel Compiler Collection suite, and both of those packages have Fortran compiler in them. So GCC has a Fortran compiler called gfortran, and Intel compiler has a Fortran compiler called ifort. Both of them are used pretty much the same way. We'll talk about differences and when to use either of these compilers tomorrow. For the sake of consistency, let's all use this GCC 481 version of Fortran. Right? So if you go to Palmetto, you can clone this repository and load the GCC module, try to compile a file, and you'll be able to run this program. So let's quickly do that, and we'll see if this works. Okay, if I create myself try to clone this repository. Should have file. Hello, already present here. Oops. Okay, and we can load module GCC 481. Type G Fortran. Hello F90. Oh, hello. .x. Enter. Don't get any message, but there should be a file hello.x present now. And you can safely execute it, .hello.x, and you get the most basic Fortran program compiled and executed. See. If this works, most of the things will work. All right, so we just compiled this very simple program, and let's see what actually happened. Very complicated thing happened in the background, and you don't, for writing very simple programs, you don't need to really understand it, but once you go even to compilation of packages that were written in Fortran or in any other language, you may want to understand what's actually happening behind the scenes. And so if you're given a Fortran code, we'll start with this hello.f90. What actually compiler does is several steps. And each of these steps can be controlled. Each of these steps can be modified and stop after. And you can look at every single middle point. So first thing that compiler does is to run preprocessor. Preprocessor is an external part of the compiler that doesn't actually translate the language doesn't translate the file from human readable to machine readable. It only takes the code and executes all the directives which say replace certain lines or certain strings in the file by something we want, or modify the file by including some other files as part of it. It doesn't do anything else. So from very short program, we may end up in something more complicated after running the processor. After that, after running this proper preprocessor, compilers usually work this way, that they have its own internal module that does the translation from one language, from human readable language to machine readable language, and then they have front ends that are specific to given language. So usually they translate Fortran, C, C++, anything else to some internal build syntax, and then they translate that syntax. That's how people are able to provide many different front ends and support many different languages in one file. So that's what happens in GCC. After that, the program is compiled, and this is the most time-consuming part. From this preprocessed file, we get the assembly file, and that the compilation is only translating the language, the real Fortran language, preprocessed Fortran language to assembly language. After that, we run the assembler that actually creates the binary readable binary object .o file, and after that, all object files need to go to linker, and linker needs to take the object file we passed together with every single dependency. So if we used any function that we didn't define, like print, we use print, there needs to be something passed to the linker that tells it where the print is really located, how it's defined, how it's used, what's the body of this function, and the linker will bring them together and create the executable file. So with this command, gfortran hello.f90-o hello.x, we actually went through this whole process. If you will be compiling bigger packages that are written in Fortran, you may be required to pass different variables during the compilation, and usually those things are passed using a preprocessor. If you will be doing a lot of performance programming, targeting really, you do want to take advantage of the 100% flops from the system. You will be looking at the assembly code and modifying the assembly code. If you just try to compile something and use external functions, you need to modify what is linked. You need to provide all the libraries that are needed, whether that's BLAS, LAPACK, fast Fourier transform, any other mathematical thing. You need to actually point your program to where those functions are located. Okay, any questions? If not, then let's go through variables, right? All variables need to be defined. It's not like some languages that you don't need to define variables, and you can create. They are created the first time you use it. So, for example, in Python, you don't need to define variables. Variables are created as you go. So the first time you use a variable, it is created. That's not what happens in Fortran. You actually need part of the code devoted only to definition of all variables that you will be using. And you may look at older Fortran codes. This is not done. We'll go through that in a second. Why it's not done? Don't rely on it. You actually need to define absolutely everything. So whatever variable, whatever type you want to use in the body of the code, you need to define at the top of the file. It is different than in C, C++, where you can create variables whenever you need in the middle of the code. In Fortran, you actually need to define them at the top. Right? And you use it by saying, what's the type of the variable? You put 2 columns, and then the name of the variable. And that's it. That's the definition. How does the definition of the variable look like? There are different types. We'll touch on that in a second. You can create variables, assign them, print them. That's a simple program to do that. After you run it, you will see what is really happening. Conditionals. The simplest conditional in Fortran looks like this. If we open we open parentheses, then some logical expression, doesn't matter how long it is, it can be a very long logical sentence. It has to, after evaluation, it has to take one of the 2 values, either false or true, and you can use any binary operation inside, any binary logical operation inside, and it really can be very, very long sentence. After evaluating, it will be evaluated from the left to the right, and after evaluation, it has to take one of these 2 variables, one of these 2 values, true or false. When this is true, then it will be executed some part, otherwise another part of the code. And we end everything using end if. Some compilers are more forgiving than others, and often you may see that things can really be closed by just end word. It is good practice to keep what is ended. It just makes it more readable. Compilers will often forgive you for not putting that in, but it really, if this is, a lot of things are ended the same way. For example, end if, end program, you may have a lot of ends, and this immediately tells you what you're ending. All right, so we have a conditional, we have a loop. Fortran doesn't have a concept of a for loop. It calls it something different. It calls it a do loop. And Fortran now has several types of loops. The do loop is equivalent of the for loop from other languages. So you will create some body of that needs to be executed for some number of variables, some range of variables, and you will iterate through that range and execute the body of the code for a number of values. So you start body of the loop using word do, assign the iterator that needs to be variable that has been created before, its initial value and its maximum value. If you define it, this is the most basic definition of a do loop. If you define it this way, the increment of an iterator will be 1. You can actually put one more comma and define what's the increment of the iterator. So the iterator is the I here. And then the body, whatever you need to execute more than once, you end everything saying end. That's the most simple loop. Yes?
Is this like Python or something where the indentation is important, or is this just?
So the indentation doesn't really matter in Fortran. It's truly irrelevant. And there are more irrelevant things in Fortran that we'll go through a second. Indentation is part of the good programming practice. You should do it. It makes code really easy to read. If you skip it, that's a mess. We're again in the fixed format thing that's not easy to read. The only important thing is that you need to end everything with words and what you're ending. Yes?
Third line there. There's an integer, there's variable max value, types integer, and then it assigns an initial value.
Yes.
You couldn't do that before, right? You need a data statement.
In Fortran 77, you couldn't do it in earlier Fortrans. Now you can.
Okay, so you do it all in one.
Yes. Any other questions? So all of those programs that I'm showing here are part of the repository. If you want to try and compile them yourself, go ahead. They have the names, loops. This one will have name loops. And you may try them. All right, functions. What's a function? Fortran has two, comparing to other languages, it has two concepts. One is called the function and one is called the subroutine. In other languages than Fortran, let's say in C or in Python, they would be exactly the same. The difference between would be this. Function would be equivalent of mathematical function that returns a value. A subroutine would be some external function that doesn't return a value. It's just an extra little program that you execute on a side. So Fortran has this distinction, and there is a reason for that. Functions first return a value and can be what we call inlined. Can be the body of the function can be inserted in the code. The subroutines really are a little bit different, and there are programs that reside on the side. So the function can be defined this way. Again, we write our program, the whole body of the program, starting with the beginning sentence, program, its name, end program, its name, somebody that will be executed, and somewhere in between, we define a region of the code and say that this program contains the thing that you need to be executed and something extra. And you use it by putting this word contains. And here we define function. And first thing we're putting here, the definition of a function is really flexible. It doesn't need to be done this way. This is only an example. The mandatory part is this. Function, keyword saying that we are defining a function, its name, its parameters, and what will be the result of this function. And it needs to end with the same end, function, and name. So all blocks of code in Fortran look a little bit similar. They start with some keyword and they end with the keyword end, and that thing that started it. So if do function are exactly program are exactly the same. Say what you're starting and you're ending it with saying end that thing. Inside the body of the function, again, it looks like its own program. All the variables need to be defined at the top. Some body of work is at the bottom, and the thing that was specified as a result, output in my case, which is either assigned as true or false here, is returned. So the variable output here has not been defined at the top, but it has been defined here. We're saying that there is a variable that will be returned, that will be a result of this function called output, and the whole function has a type logic. So that will define automatically a variable called output. So if you do it this way, this is equivalent with defining that variable at the top of the file. We'll see how it's done in different ways a little bit later. All right, so here we have a simple function. Subroutine, it's a little different. It is a special thing that doesn't return anything, doesn't return a value. So it's not equivalent of a mathematical function. If it's, it is equivalent to an order saying, all right, you do something, but I don't necessarily need to see one single value of that. There needs to be some work done. And it looks very similar. The name is different. The name is subroutine. Again, it ends with end subroutine. The body is inside. Nothing is returned. There is no value, no result of that. There is only some work. So in my case, this subroutine will print something, but will not bring back a single value. And we didn't really say how the function is executed. So I define a function, and I execute it this way. My function was called sign test. It took some input and it returned some output, some value, and I execute it this way. Name of the function, all the parameters, and it gives me some value, so I can assign immediately to some variable. The subroutines are executed a little different. We define the subroutine, and then we can use it by calling it. We use a keyword call and the name of the subroutine with all of its parameters, and this means execute that block of code. Either return, take all the initial values and don't bring any value back. Any questions? Yes?
Function inside the program, but subroutine is outside.
You can do it both ways. Don't. The way I did it, the functions, since the function is returning a value, it looks like a variable. After you execute a function, it is a variable. So that variable needs to be part of the program. And you can do it this way. You can say this program contains that variable that is truly a function. In subroutine, it's not really a variable. It's just some extra code. It doesn't need to be part of the program. Now, the function doesn't need to be part of the program either. You can specify at the beginning that, right, you will be using something that's important called external variable, which will be function that's defined somewhere else, not as part of this of the main program. So that's generally how you write subroutines. It can be also part of this block here. It can be part of the contain. It doesn't have to. And we will go through more details when we talk about functions and subroutines in a second.
The main difference is that the function returns a value, but
Correct.
subroutine doesn't.
Correct. So if you're comfortable with C, for example, or in Python, in C there is this type of function called void that doesn't return anything. It returns void, and any other function returns some value. In Python, that would be a function that really doesn't return anything. Here, there are these two concepts. You can use a function and return either some error value if you encounter one, but you need to return something. And you don't need to collect it, but every time you execute a function without collecting its value, that value is actually returned. So let's say you have the same body of code and you try to execute it by function and by subroutine. The function you need to define what will be the type that is returned. It can be the simplest one, but when you execute it over and over and over and over and over and over again, every time you execute it, this function is actually returned. This value is returned, and it takes some memory. It's created and it takes some memory. In the subroutine, there is nothing returned and nothing takes memory. There is a concept of something that's called the garbage collector. So whenever you execute something and you don't use it, that values are destroyed. Fortran does not have that. The Fortran does not have a garbage collector. So for example, in Python, when you execute the Python code, or R code, those languages have built-in garbage collectors, and they deal with things like that. Fortran, since you compile the code, you said, all right, I want to do it this way, and from the compilation to forever after you want to run this program, it is done this way. The compiler may correct a lot of things for you, but not things related to. It will not do things behind your back. You may expect that you will be using that variable a little bit later. Any other questions? We'll go through details of subroutines and functions later. Here we're just running through everything we need, through these 5 concepts we need to run a program, to write a Python program. All right, a few more things. Fortran is case not insensitive. Everything name of a variable can be capital, started with capital, started with small letter, it can be all capital, it does not matter. Fortran is case insensitive. Fortran also removes all white characters when you compile the code. So if you use space in the middle of the name of variable, it doesn't matter. It is correct name for a variable. That white space will be removed. So you can call things my variable or my space variable, and they will be the same. There will be valid things. This is about thing about Fortran that it does not care about white characters. You can have names very long with spaces inside that confuses people from other languages, but it is valid Fortran things. Very large Fortran programs are usually split into modules. We'll say what's a module later. Think about it as a separate part that may be portable between 2 different programs. It is a way of isolating one part of the program and not confusing it with other programs. Okay. In modern Fortran language, every line that starts with exclamation point is a comment. In Fortran 1995, there is a free format, but it may be compiler specific. It's not really as long line as you want. It is only 135 characters, and you need to tell the compiler that to pay attention to things that are beyond that limit. So keep in mind that if you get an error and you're sure that your code is fine, there may be this limit of 135 characters in a line, and then you need to say to tell compiler with the switch, okay, don't care about this, compile everything. So there are still some parts of Fortran that are like that. All right, best programming practices related to Fortran or any other language. Code formatting is the most crucial thing. Fortran will remove every single white character in the code. So you can start writing that way. You can write something that will look like very compressed text file without any space, without any indentation, which will be unreadable for people, but that's how Fortran will really execute. Comments. I give this value, a third of the code should be comments. And it's not for other people, it's for yourself. As good, you may be the best in programming, you may understand your code extremely well, week after, month after, people forget. It has to be documented. And so please use some documentation way of, some way of automatic documentation of your code. There are external packages that will document the code for you. They will not augment the code itself. They will rely on some hints from the code. But if you're developing some bigger project with other people, you need to document it. Pay attention to packages like Doxygen that will do the work for you. They will build documentation. Names of variables, functions, subroutines, they should be meaningful. They should not be A001, A002, and so on. They should mean something. They should mean something to you and should mean something to other people. So if you have some physical model, make them look like they're part of they relate to equations. I was working in a project where a person didn't really wanted to share his code, but because he believed that the code needs to be shared, but or that was a requirement from a journal, I think, and but he didn't want this code to be modified and used for other things. So he replaced all the variables with some random characters, and the code worked, but it was not really readable. So don't do things like that. Make things readable for yourself. Use a revision control system. Use a code like CVS, SVN, Git, or Mercurial, or any other package that will check the versions for you and keep track of changes. Make a lot of test cases. If you're building larger project, it is very easy to make a mistake that will make the program work, but will give wrong values. Make test cases and write yourself a little program that will validate the results. So if you're writing any meaningful program that needs to do some simulations, needs to do some meaningful work, that come up with test cases that will always return the same value. And every time you make a serious change to your code, not implementing a new things that don't touch other places, but changing existing code, run these test cases. Make sure that you get exactly the same value, 2 digits. It's really important. After that, whenever you compile your program on different machine, make sure you run these test cases. You get exactly the same value, and it needs to be exactly the same value. Computers are really, the results should be reproducible, and if they're not, something bad happens. Unless it is by design. Make the program also compiled automatically. Use make files. We'll talk about that later. And you don't need to compile things by hand. All right, so we'll go to data types. It's 10:06. Let's make a 5-minute break, and then we'll go through data types. All right, let's resume and start talking about different data types. Um, as we said, all variables need to be defined before they're used, and all variables need to have a type assigned to them. And from that moment, they're created, and the type cannot be modified. So there is several obvious data types. The basic one, integer and real. All of them, all data types can be divided into just integer or real types. And to define an integer value, to the variable, you need to use a keyword integer, then 2 colons, and define the names of variable. You can specify that variable that will have a constant value, not being able to be modified through the course of execution by using keywords parameter. So for example, a physical constant, something that truly should not change, even by accident, you can say, all right, this will be a parameter and you cannot change it. You can assign value of variable in the definition or after. It doesn't need to be, you have flexibility to do it. Real values, all the Fortrans brought concepts of a real value and double precision value. And there is this distinction of a real and double precision, or sometimes called single precision and double precision. They're both real values. It's the distinction is in the how many digits are stored and are correct. This is a little bit simplified version of what should be really said. The length of the number is greater. And the real value comparing or single precision value comparing to double precision value stores shorter number in the way computers handles numbers, and that gives a less precise value. Fortran really is a little bit more than integer and real. It has also a built-in complex numbers. You can define that the same way as you define real or integer value, and it always defines a pair of numbers, real and imaginary part. When you assign them, you need to assign both of them. Otherwise, you will only assign the real part. Character values, they're defined using keyword character, 2 colons, and the name. Then that will be single character. You can also specify strings that will be characters of a given character variables of length longer than 1, and you specify the length of this character of the string, saying len is equal to 100, and this value is now able to store 100 characters. Right? And the logical values, same way as any other before, they can only take true or false value assigned using keyword, created using keyword logic. So these 5 basic types, integer, real, character, logical, and complex are built in into Fortran. You can either assign values immediately to a variable, or you can assign values when you need to use them. Sometimes the good practice is to either always create a variable and assign its value to something neutral, either 0 or 1, or rely on compiler's assignment of the values. Don't make assumption that everything will be assigned to 0 for you, that every variable will be assigned to 0. Especially if you deal with bigger structures like matrices or tensors, don't assume that those values are automatically assigned. Do it by hand or rely on compiler flag to do it for you. Don't take assumptions what compiler does by default. Right, and all the arithmetic operations that are binary can be summarized using this table. So power is defined, multiplication is defined, division, addition, subtraction, merging strings for characters, relational operators. You can use the new syntax or the old Fortran 77 legacy syntax. So if you want to compare things, if you want to see if something is greater than, you can use the greater than sign, or this Fortran notation dot gt dot stands for greater than. And that's common in Fortran. You see it also in definition of logical variables. There is not only a value true, but it ends. It is encapsulated by 2 dots. This is because Fortran does remove the white spaces, and if you all the keywords that are meaningful and also can be part of a name, like true or false, should look a little bit different, and that's why there are dots. Just to distinguish them from a variable. All right, so there is this .gt, .lt for lower than, greater or equal, GE, lower or equal, just equals, EQ, non-equal, NE, and similar for logical operators. There is dot not dot, dot end dot, dot or dot, dot EQV dot for equivalent, dot non-equivalent, and EQ dot. So that's a little bit different than in other languages. All right, the distinction between single and double precision. This is true for valid point for all languages that are compilable. That you need a compiler and you need to define variables and you need to think what will be single precision, what will be double precision. For almost all scientific applications, you'll be using double precision or higher. It's a safer assumption than saying single precision can be automatically used. You need to actually do some testing whether single precision is good enough for you. But after that, when you know what type to use, you need to proceed with that. Fortran started removing the concept of having different keywords for different precision and treating everything as a real number. So whether it's a single, double, quadruple, or higher precision, it is still a real number and should have that name and treat it as a little bit more generalized real number. And the same with integers. There is different type of integers there. Even in any other languages, there is always many types. Ones are shorter, ones are longer, ones take more memory, some take less memory. And in Fortran, now they're all integers. They're all integer value, and as a parameter of this variable, you can specify what kind of integer is that, what kind of real value is that. Is it a single, double, quadruple, and so on precision? That's where the unification of all real numbers and all integers started, and you can define by default real values A and B, and say, all right, I'll call everything real. And then I'll tell the compiler to treat every real value as either single, double, or quadruple precision. You can do that. Or you can by hand, you can not rely on the compiler and say, all right, I actually want to select that these particular real values are single precision. and other values are double precision. But I want to keep it flexible. I want to be able to change between. So this lets you define a parameter that will define the precision, and you use it by using a function that calls is called selected real kind or selected integer kind. And this, as a parameter, takes number of digits that should be correct. So in our case, 15 digits should be correct for a double precision value. And then when we create a real value, the same way as A and B, we define them the same, but in the definition of the real, we put kind is equal to that defined, previously defined integer value that defines the kind of a real number. And there is, if you were using Fortran 77, before that was possible there, you didn't have to type single precision, double precision, real. You could just type real star 4, real star 8, real, and that was it. That means that real value was 8-bit, 4-bit long, 4-byte long, and was called a word, a real word. And the same with double precision, it was 8-byte long and wide, and that was called a word. A lot of legacy codes still use that concept of a word as a memory counter. All right, so you can, in case you want to use both single precision and double precision in your program, you can define yourself a piece of code that we call module. And that will be portable between different parts of your code. And we define it by saying module and some name, and then what needs to be defined and what needs to be portable between these different parts of code. So we'll say implicit none. I'll explain what that means in a second. And then here we define two integer values, both as parameters. One will be called SP, and will select real kind equal to 6 digits, requesting 6 digits. That will be single precision value. The other one, DP, for double precision, will select real kind of length 15. Okay, so we created ourselves a module, and that creates a portable part of code that you can take, and everything defined inside is not used anywhere else by default. You need to actually say, all right, I want to use some values from there. I want to, and some other parts of code don't need to use them. So whenever you want to use values from that module, you need to put this sentence, use and the name of your module, and that will make all variables from that module available to the rest of the program, to that part of code. Either that's this main program, or it's a function, or it's a subroutine. You can pass variables in groups. Older versions of Fortran had something that was called a common block. That was hated by everybody, and was very, very difficult to maintain. The modules are supposed to fix that, and they're much more flexible than common block. All right, so if you actually compile this program, we should see different length of numbers that we created, and single precision should be much shorter than double precision. All right. Fortran also brings concept of higher precisions, like quadruple precision. That's built into Fortran. You can also select a range of real numbers that you want to use. In real applications, you may be using only these modules, this types of real numbers that will create either single, double, or quadruple precision numbers, and it is good practice to do it this way. The higher precision of a number you use, the bigger range of numbers will be available to you. So it's not only that you need numbers to be precise, to use higher, longer numbers, wider numbers. It is also when you go to very big numbers or very small numbers that the story matters, because of the range and because of the precision. Fortran introduced something that was called IN rule. So people at the beginning didn't like Assam creating, so they said, all right, we don't want to spend time assigning different values, different types to different variables, and people that created Fortran said, we'll make something that will be called IN rule. And this was in Fortran 77 or earlier versions of Fortran. This was used by everybody. Nobody really liked defining types of variables. So what IN rule, and was enabled by default. So IN rule in Fortran says this: everything from I to N everything that its variable name starts from a letter between I and N will be an integer. Everything else will be a real value. And at that point, if you just define, say, I is equal 1, you can rely on the IN rule, and I will be automatically integer. If you want a real value, it has to start with different number, different letter than between I and N. It has to start with something else. And that will make, if you define A is equal 3, that will be a real number. Okay, so that's the IN rule that makes things confusing. Let's actually see how this works. So in this program, in the repository, you have a file called i-n-rule.f90. And it is exactly the program I showed. It has one more line at the top that says implicit no. And we'll comment it for a second. So now it looks exactly as something I showed you. I equal 1, and then print I, A equal 3, and then print A. And let's see what happens. We didn't define any variable. Hope hell can get that unleashed. Let's see. Okay, G Fortran, IN rule, OI. It worked. When we try to execute it, it also works. So we did not define any variable, but we start using them exactly as we would do in Python, and it actually worked. It is very confusing to read bigger code that relies on this rule, and we have also no little control over the variables. So it is a good practice now to say, forget about the IN rule. We'll do everything by hand. And this is done by introducing this line, implicit none, which gets rid of the IN rule. If we uncomment it, that will implicit that no variable is defined automatically. If we try to compile it again now, we get an error. So symbol A at 1 has no implicit type, symbol I has no implicit type, and we need to actually say define. So that's IN rule in Fortran. Okay, that's the same what we just did. Newer versions of Fortran bring a module called ISO Fortran ENV that brings definitions of single, double, and quadruple precisions as real 32, real 64, and real 128. So if you want to rely on this built-in module versus defining precisions by yourself, you can say use intrinsic module ISO Fortran ENV, and you can define yourself this single precision, double precision, quadruple precision values that will define these kinds. Real 32, real 64, and real 128, and those will be numbers of that byte, either 4 byte, 8 byte, or 16 byte. Intrinsic means that this Fortran has been brought by the compiler and it's already available to you. You don't need to make it yourself. Right? There is also, since we have many different types, there is also a basic type conversion functions, and you can convert variables from one type to another. So, for example, the function real, double, int, or complex CMPLX converts values from whatever it's the input to real number, double precision number, integer number, and so on and so on. When it's needed, rarely in the program you will need to convert numbers from one precision to another, but it is needed whenever you read input parameters. So if you pass input parameters to a program, they're always passed as characters, they're passed as strings. And then if you want to use a number that's passed as an argument, you need to actually convert it to a number, convert it to real, integer, and so on. The same with files. If you read it from a file and you don't implicitly say that whatever I'm reading is that double precision number, you need to convert it to a number. All right? Any questions? All right, loops. The most basic loop is a do loop, and Fortran 77 up to Fortran 90, we only had a do loop. We didn't have anything else. Other languages bring more loop statements. There is a do loop or for loop. There is a while loop and until loop statements that are a little bit different. They're not based on counters. They're based on logical expressions, and they're either checked at the beginning or the end. Now Fortran has all of those, but it turns out that the do loop or for loop is the only thing you need. So to keep things simple, Fortran's most used loop is a for loop equivalent, it's called do. And it starts with this statement do, and then our iterator name, the variable name that will change, is equal its initial name, initial value, final value, and the step. And then the body of the loop, everything has to end with end do. And as you see, it can be either end space do or just end do, or it can be much longer. All characters can be really divided into whatever you want. Fortran will remove any white spaces. The last parameter, step, is optional. You don't need to specify it. If you don't specify it, the default value of a step or the increment is equal 1. So the very simple compact form do I is equal initial value, final value, All right, so simple do loop would look like that. We implicitly say don't assume any type of variables. Then we create an integer values called I, max I, and I step, and we want to run the loop from 1 to the maximum value with given step, and we assign these values to as max I and what's the step, and then we run the for loop, just printing every single value of the iterator. Is
The value of I
after the do statement, after here, let's see. All right, so we have exactly the same program. Let's try to execute it, compile it first. Fortran do loop. That gives us 13579. So let's do step as 1. Let's try to compile it one more time. Now we go, the default, the last value that's assigned is 10. And let's go behind the loop body and do print I. So it is 11. At the end of the loop, what really happens is this. The top of the loop also executes logical expression. And whenever the iterator is greater than our maximum value, the loop is broken. That's why there is a higher value available after the loop. That's exactly like in C, exactly like in any other languages. There is a logical expression there. Yes.
I go down. I go from 10 down to 1.
All right, so let's do min I is equal, let's say 10, 1, step will be -1, here we do min I, and we'll do min I, max I step. All right, so this will be actually, we'll go from the minimum value, or from, let's call it different. Start I, end I, and I step. Then we'll change to start I, end I. And we'll do the same here. Start I, end I step. Like this. Is that not what you expected?
That's what it should do.
That's what it should do.
Makes more sense.
So it started from the initial value of I was start I, which is 10. It started with that one and it printed that value first. Yes. Then it changed the value the I by this. So it added -1. And that's why we had 9 as a second value.
This time it says it's less than Wait, when the iterator was less than
Yes. So it actually so
wait, when it was greater than
yes, because it checks whether they are in this interval. And it automatically, you don't, in languages like C, you would have to say, okay, here is check using that logical operator. Here it checks the range, it switches. Is that clear? Okay, there is also while loop now in Fortran, where there is clearly a logical condition to check. So the body of a while loop executes some part of the code as long as the condition is true. So, for example, we can calculate the factorial using while loop and starting multiplying values from the absolute value of a number and decreasing until 1 or until 0 and checking whether we increased, we still need to multiply or not, and that will create that can be easily done using while. All right, writing an infinite loop in Fortran is trivial. Actually, no initial values, no final values are needed. The most basic loop is this. It will say do somebody and end to, and that will execute forever. So you can this may seem to be not useful, but it actually is. You can always do this. Gives you a lot of flexibility. As long as you create an infinite loop, you can do inside whatever you need. And that was a way of creating while loops and until loops without clearly defining them as a part of the language. At any moment, the body of the loop can break from being an infinite using an exit keyword. All right. So the loop breaking may do this way, maybe done this way. You can use exit at any moment. You don't need to go to the end of the loop. Let's say you're solving some equations, you truly iterating over some meaningful values, and you want to simulate the until or the while loop. But the while loop is not really suitable for that, for your case. You can have a logical. You can have a conditional inside your loop and check the value of iterator based on the value or some other value inside the body of the loop, and you can use exit keyword to break out of the loop. So, for example, here we'll run from 1 to 10. We'll be summing up to some other value, and if that value is larger than some threshold, we'll exit before the end of the loop. Right? There can be also an until loop. I'm sorry for that. There is also an until loop that looks like it doesn't have its own keyword. It's not a specific. It's not explicitly until loop. It is a modification of the do loop, of an infinite do loop, together with a logical expression and an exit value at the end. Looking like that. If you see something like that, this is an until loop. And the logical expression can be anywhere. If it's at the beginning, that will make it a while loop. If it's at the end, something else. Right? You can skip a cycle. You can skip a given value of operator, and that does not. There is a word cycle to do that, which means that if you use it, you will not exit the loop. You will not terminate the whole loop structure. You will only terminate that particular instance, that particular iteration of the loop. So if we have the same example as before, we're iterating from 1 to 10, And we have some logical sentence here. After that, if that's true, use the word cycle. We'll only skip print for iteration number 5. Will not break out of the whole thing. Using word exit, will break out of the whole loop. Using cycle, will only skip that element. So you can, for example, this doesn't have to be iterator, it can be any other variable. And based on the value, you can either do something or not, but you have some assumptions of how big work should be. There is a nice statement that is very useful for performance programming. It's called for all, and it's truly independent loop. So it takes this syntax for all, some variable in its initial value, some final value, and iterate, and the step is optional. Do some body of work. This tells the compiler or tells the program that you have some work that can be done truly independently. And it looks like a do loop, but it doesn't have to be done one after another. It can be done all at the same time. So an example program to do it. It also shows how to write loops as one line. First, we'll create some variable called a that will represent a matrix. And for that, we'll create a real variable a. We'll use 2 more keywords. One will be called allocatable, and another one will specify dimensions. So from a single scalar, we will define a shape of this value as 2 columns separated by comma. That will create as a matrix. If it was like one column, there will be a vector. 3 columns, it's a 3-dimensional tensor, third rank tensor, and so on up to serial number 7. And after that, when we use this keyword allocatable, that means that at this moment only the shape of the variable is created. The real memory has not been assigned. You can assign it later. And you have to do it using allocate word, and you say what is the actual size of the array. So we will say that we'll also create some integer value n here and assign it as 100. So at this moment, we'll know that size of this array will be 100 by 100, and we'll allocate the given memory to store that array. After that, we'll try to assign some values. So for all elements from 1 to n, so from 1 to 100, we'll set the diagonal elements to 1, and the rest will be unset. We can do that as we know that this process is truly independent. We can do all at once. And please, if you have that work, take advantage of the for all statement. It automatically tells the compiler that you have a do loop or for loop that has no dependencies between iterations, and the compiler can do all crazy things to make it optimal. If you have something like that, this is a way to take advantage of the compiler's optimizations. All right, conditionals. The if conditional, we already saw it. It has this simple structure. We used it several times already. Let me go back, and I wanted to say one more thing. We use this loop this for all type of loop a little bit different than before. We didn't have end for all here, and this is valid whenever your loop has one line. So if it is only one line of body, you don't need to say end for all at the end. You can use a one-line form of this statement, which means you use the for all or do or if any keyword that has the same form. It's conditional and then the body. And if it's one line, you don't need to end it with end given structure. All right. So if conditional, it takes a logical expression and executes the body. If that's true, then it can be combined with else keyword, and you can have an alternative body of text for different case. Right. So the simplest case of using that is this program if conditional. We implicitly we say that to implicit non-variables, we use real value type for variable called val. Then we call a random number generator function that's built into Fortran and assign this value a random value. And based on the value of this number, we either print that it is larger than half or smaller than half. And that's it. The random number function will generate a single value in the range 0 to 1, and it's built into the language. Okay, the conditional can be more complex, and it can include a lot of combined if else blocks. Each of them requires then its own conditional statement, its own logical sentence to be evaluated, but can be as long as you truly want. There is still part of Fortran as its backwards compatibility. This syntax. You can in Fortran 77 or earlier Fortrans, you were relying on assigning, relying on everything, every line starting with particular column, and earlier columns were reserved for line numbers. So you can still assign line given number and use this line numbers later for code execution. So that can be used in the if statement, and you can have some variable, and based on its value, you can go to either line X, line Y, or line Z, some line in the code, and then you have to actually mark your code with line numbers, and this will be executed. Let me see if I have an example. This will be executed the logical expression will be evaluated, and this needs to be a number now. And if it's smaller than 0, larger than 0, or 0, you will go to a particular line. So let's look at an example. We have a small program that calls one subroutine that checks value, and we implicit non. We create 3 integer values. One will be called take value -1, next 0, and next +1, and we'll check its value. And in this subroutine that checks the value, we'll use this conditional that has this weird form. If value, then go to 20, or 30. Now, line 10 will be defined print, and this sentence value is smaller than 0. After that, we cannot simply proceed with the rest of the code because we don't want to execute that. We can go to a particular line of the code later, skipping some code ahead. And we go to somewhere else, we can print here some statement, or we can just use the word continue to proceed with later part of the code. So the same, when the value is equal 0, we'll go to line number 20. When it's larger than 0, we'll go to line number 30. That will execute and print this output. There's also a case conditional. If you have blocks of nested if-else conditionals, you can replace everything to make it a little bit more readable with case conditional, and that takes this form. There's select keyword followed by case, variable, and different cases for different values of this variable. So if it takes value 1, you will execute this block. If it takes value 2, you execute this block. If it takes value 3, you execute this block, and so on and so on. There is a default case if it takes value that was unexpected. All right, and the example looks like this. We'll take a single value and we'll check if it's equal 1, 2, 3. We'll print something. If it's not equal to one of these three cases, it will proceed to the default case and do something better. All right, so any questions? We'll run through the whole Fortran. You actually should be able to program in Fortran now. We went through all these 5 concepts in very quickly, and we actually said that there is only 5 things you need to learn. How does the basic program look like? And that's the hello world. There's nothing more basic. There is something more basic than that, but that's actually the only usable basic program. We went through how to create variables. We talked about variables. We talked about conditionals.